I'm very happy to announce Dustin Clausen from IHES. He will tell us about the K-theory of the complex numbers.
Oh, thank you. It's very nice to be here giving a talk. So this is about K-theory of the complex numbers, and it's a joint work with Peter Scholze. It's kind of very, there's no big theorems or anything. It's kind of a long-term project of mine. Basically, the goal was to ask the right question. And then maybe the answer, well, I don't know when the answer might come, but maybe someone, yeah, we'll see. So I hope at least I'll ask the right question by the end of the talk. So let me, by way of background, let me start with a reminder about algebraic K-theory before specializing to the case of the complex numbers, talk about the general situation. So let's say we have, well, maybe not too general. I'm going to take a ring, but I'm going to assume it's commutative. And there's two reasons for that. One is that later on in the talk, some kind of tensor product will be important. And the second reason is that I don't have to say left or right. So then I recall that K0 of R, you take the free abelian group on the set of finitely generated projective R modules, and you mod out by some relations, which says that you set this equal to this if there exists an isomorphism from M to N direct sum T. This is kind of the familiar thing. So you, kind of the universal place where dimension-like invariants reside. Things, the invariants that are additive in short exact sequences. But I'm not just interested in K0. There's a reason why the zero is there, the classical algebraic K-theory, but I'm also interested in the higher algebraic K-theory. And the story there is that, in fact, there is a, you could say, homotopy type, canonical, called K of R, with pi 0 of K of R equal to this classical thing. And I won't give you a precise definition of this homotopy type. Instead, I'll tell you things. For example, one thing I can tell you is that you can think of kind of, so this homotopy type, it doesn't, so you have a set of components, the pi 0, which is the usual K0, but then you also have this pi 1. Let's say you gained an understanding of K0, so you maybe have some list of representatives for all, or list of elements in this K0 group, and then you give yourself a finitely generated projective R module, then you have some understanding of how to equate it with something in this list. But maybe there's different ways you can, using these relations, move your module around to get it to equal to one of the representatives in that list. And you can kind of, if you squint enough, you'll see yourself tracing some sort of path in some space. And then maybe you can also trace loops in that space. And that's kind of what pi 1 would be. And you can try to identify K1 in that manner. And then if you identified K1, there may be some ambiguities in how you identified representatives for all the loops, and that would give you something like K2 and so on. And you can make this into a formal definition, and even more miraculously, with lots of hard work, sometimes you can even calculate these K groups in very simple cases. Okay, and that's one thing I wanted to say about these higher K groups. Another thing I want to say is to give an example of fields. So if R equals K is a field, simplest thing, then there's something we all know, that finite dimensional vector spaces are classified by their dimension. Since we group completed, that gives us integers. K1 of K is K cross. So that's the ambiguity in fixing a one-dimensional vector space. But it turns out that up to some simple rules, the ambiguity in fixing an arbitrary dimensional vector space reduces to that in a one-dimensional vector space, meaning you get K cross. And then the fun thing is you can actually give a presentation for K2. This is called Matsumoto's presentation. Well, now it gets a bit more involved. So here implicitly, I'm using some multiplicative structure, but okay. So so you take the, okay, this is an abelian group under multiplication. So I think of it additively, actually. In this incarnation, it's actually best thought of as an additive group. And you take that tensor product with itself as abelian groups, and then you mod out by a single family of relations called the Steinberg relations. They're parameterized by elements of the field different from 0 and 1. And you get some big group this way. And that turns out to be what K2 is. And it's a little bit more tricky to give explicit descriptions once you go farther down the line. I mean, for general K. Okay, that's another thing I wanted to tell you. The next thing I want to tell you, or ask, with that we'll ask the question together, is why do we care? Why do we care about higher algebraic K theory? Well, probably there are many different reasons, but there's one that's maybe closest to my heart that I certainly want to mention, which is that, well, K theory is strongly related to something called motivic cohomology. And motivic cohomology is strongly related to something perhaps conjectural, which is X groups, or maybe it's equal to, I don't know, in some category of mixed motives. And these they're realization functors. And you get things like X in Galois representations, or if you're over the complex numbers, X in mixed Hodge structures, whatever other realizations you have. And so what you can think of K theory class as kind of a, well, it's motivic in the sense that it is a universal source for the kind of data you might see here, an extension of Galois representations, extension of mixed Hodge structures, kind of one object that gives rise to all those different things in different worlds. That's one aspect, but the other aspect, but that would be not worth much if there weren't some reason why this could be understood. And there is a very good reason why this can be understood, and it's that K theory is basically just linear algebra, just linear algebra. I mean, it's all just about vector space, finite dimensional vector space. You take the category of finite dimensional vector spaces, you do something with it, but in the end, it's just linear algebra, right? So that actually does make it easier to study in many ways. For example, to understand this, you need to know not just linear algebra, you need to know about things like polynomials. Those are complicated. Yeah, but somehow there's a relation. Okay. I wrote some things here. I wrote valence in here. And oh yes, and I wanted to say this actually kind of works. I mean, I think the only reason we know things about X in mixed tape motives over the rational numbers, for example, is because we can understand enough about general linear groups, and GLNZ and its cohomology due to Quillen and Borel-Serre. So really, I mean, this path of going from linear algebra to this kind of fancy stuff actually works, at least in some cases. Okay. So then coming back to KFC, well, when I said that, it sounded like KFC. Okay. All right. I'll be here all week. So this, whatever this is, it should have to do with following this Valenson line here. Should have to do with cohomology theories over the complex numbers. That's what we're interested in probing here when we talk about the K theory of complex numbers. Okay. Any questions?
Orgy theories of what?
Details come later. in principle algebraic varieties. But therein lies the problem. This lets me segue into the next. So what is the problem? By the way, I have a record. The first time I gave a talk about this topic was 8 years ago, almost to the day. And so I've actually been thinking about this for a long time. So what's the problem? Well, K theory, this construction K theory only refers to the abstract field C. So it's going to be the same for C as for any. So algebraically closed, characteristic 0, cardinality continuum. Right? It's going to be the same for any field with those properties. It doesn't know that T is a very special field that has a topology and attendant geometry and so on. So let's look at this more concretely. So I invite you to try to ponder the structure of this K2 group, or lack thereof, and somehow take into account the topology of the complex numbers or something else. It's really quite messy. I mean, so in fact, there's a theorem of Milnor, which is, I'll say it loosely, the maximal, you can try to put a topology on this, but in any case, the maximal Hausdorff quotient is 0. So this is a huge group, make no mistake, but it's all chaotic. So this suggests that whatever it may mean, the completed K2 should be 0. With K0 and K1, there's no problem. Z and C cross are perfectly reasonable things, but once you get to K2, things get a bit funny. But on the other hand, it can't be true that the completed, whatever it means, that the completed things should be 0 in all degrees bigger than 1, because they're regulator maps. Okay. K2n minus 1 of the complex numbers goes to C mod 2 pi I in Z, so they're regulator. And regulator maps, this being for n bigger than 0. So there are, and we know these maps are non-trivial, so they, because we map K2n minus 1 of Z in there, you get something interesting. So in odd degrees, in positive odd degrees, there should be something reasonable inside these, or some reasonable maybe quotient you can think of. It's probably not a quotient, but something reasonable that this maps to, okay? Even though in the individual groups themselves will have the same problems as in the K2 case. There'll be some wild stuff, non-Hausdorff, crazy looking things. So now I will ask the vague form of the, or present, let me say the vague form of the question, or variety of questions. Does there exist a completed variant? Completed variant of the algebraic K theory of the complex numbers, capturing regulators, how to calculate it, and what is the relation to cohomology theories? And say, is there more than just regulators? Just regulators, yeah, right. So those are the kind of questions I want to address, or no, I want to make precise, yeah. But are there any Do you have any questions for me right now? Okay.
What is the relationship to KU?
To KU? Well, KU, I mean, you know, KU is like this, just this part. Bumped up to the next degree. Well, it's like if you take the if you imagine taking the homotopy type of this, turns into a circle, that's like a z in the next degree. And that's, you've seen KU even like that. But,
does that mean the answer to is there more than just regulators will be no?
Well, I think there's an underlying false assumption behind your question, which is that this completed variant will be KU. I mean, it's definitely more refined than KU. It should map to KU, but it should be more refined. So I think that because it should see these things and not just these things in the next degree. Yeah. Did I answer your question? Yeah, maybe. Okay, maybe your question will make more sense later. Okay. Okay. So next topic is candidate complete. So let me give the basic idea. Well, what was K of C based on? Yeah, linear algebra, finite dimensional complex vector spaces. But this is bad because it only uses C as an abstract field. And then the complete thing, which I'll switch to calling an analytic thing. So this is. This will be based on certain topological C vector spaces. Let's see if I can. Remarkably difficult.
Is it possible to give a meaning to the BGL plus construction, the political sense?
Well, wait, because I'm going to pull the rug out from under your feet immediately. Well, okay, but there's a problem with this. Interpreting this too naively leads to problems, namely that so categories of interesting non-finite dimensional categories of topological vector spaces tend to have Eilenberg Swindle. So there's maybe some completed infinite direct sum of it, of any object, and if you direct sum your original thing with that, it doesn't change it. And this gives a relation x equals 1 plus x in K theory, which proves that 1 equals 0, and the whole thing has to vanish. Hilbert Hotel. Yeah. So if you interpret this too naively, your completed K theory is just going to be 0, completely, just totally 0. But so we need a new idea. And thankfully, a new brilliant idea was provided by Alexander Efimov. So this is invented a new theory of K theory, or extended the context of algebraic K theory. And let me explain how it goes. Without giving details, although I'll give more and more details as I discuss the example I care about. So at first, I won't tell you anything, but then, yeah, okay. I'll just set the stage. So what did we have? We had finite dimensional, I'm going to stick to C. Yeah, we have finite dimensional, or no, well, finitely generated projective R modules, maybe I won't. The first thing you have to do is change the context a little bit. You have to go derived. This is not the most important part of it, but it's something you do have to do to get the theory to work. So you replace this by perfect complexes of R modules. And again, there's a version of K theory. So where K0 is free abelian group generated by all perfect complexes. Another relation you write down is that the class of M equals the class of M plus the class of P if there exists a cofiber sequence. So MPM, so distinguished triangle derived category in the homotopy category. And it's the same as the K0 you had here. That's not difficult to see just by resolving your perfect complexes. So here you're thinking of universal Euler characteristics. Here you're thinking of universal dimensions. It's the same thing. And that also extends to the hierarchy. You can also define hierarchy groups here, and it also is the same as the hierarchy groups you have here. That's not as easy to see, but okay. So you want to work in this kind of derived context as a first, but then the real change comes next. So first of all, what kind of an object is this? This is, well, it's some kind of derived, small derived category. So let's say a small, and let's also say idempotent complete, stable infinity category. And now here's the cool thing. So Lurie showed that this world actually has an enlargement. The category of these kinds of categories sits naturally inside a larger category of other categories. So small, stable, idempotent complete, infinity categories. The category of those sits fully faithfully inside something called dualizable, presentable infinity categories. And then, so these are big categories. They don't have a set's worth of objects anymore. They're generated under colimits by a set's worth of objects, but they are big. And the morphisms here in this category are those colimit preserving. I apologize for my handwriting. Just listen to my words. And my writing is just there to slow me down. Colimit preserving functors with colimit preserving right adjoint. So that's a mouthful, right? Okay. And then what is this inclusion implemented by? You have a small category and you take its in category. And you can see that this condition on morphisms on the level of in categories is just the condition that means that it corresponds to a functor on the level of small categories. So it commutes with colimits, so it's determined by what it does on C. Then the condition on the right adjoint means that C has to go to D. You have such a functor from in C to in D. And the important condition is the dualizable, and this means close enough to compactly generated. And I'm not going to make that precise again until later in the talk. Suffice it to say that they're in some sense controlled by compactly generated categories, but they do not themselves have to be compactly generated. So this is what I mean when I say pulling the rug out from under your feet, because we like being compactly generated. It's great, but now I really believe we have to learn to get there. It turns out there are so many, there are interesting examples, categories people never even noticed before looking into this that do all sorts of things for you. We have to get used to not having enough compact objects. There's another reason for that. I just realized staring at Tomer in the audience, but that's for the homotopy theorists. Okay. Right. Okay. So I'm claiming, I claim these things are everywhere, but I'm not going to give an example yet. Interesting example, a non-compactly generated example. Oh, shoot. Is it normal that these boards are so difficult to move, or am I actually weak? Go ahead and answer true. What's that?
Yeah, or
they're brittle and I have one advantage though, which is I can do okay. Right. So I have to, I'm afraid this is all very abstract and I didn't even give you examples, but I have to introduce you also to a variant which actually helps to produce examples. So there's an analog of this whole story with tensor structure included. So there, I would say the thing to put on the small side is small, stable, infinity categories with symmetric monoidal tensor product, and all objects are dualizable. So again, perf R, if R is a commutative ring, is a perfectly nice example. This embeds into what are called rigid, presentable, symmetric monoidal infinity categories, stable infinity categories. These were investigated by, defined and studied by Gates, Gorey, Rosenblum. And so it's some big tensor categories, okay? And again, the functor that implements this is C goes to in C. And there's something nice over here, which is that here, you want, and morphisms here are colimit preserving tensor functors. And a nice thing here is that it automatically has a right adjoint that commutes with colimits. So that weirdness that you had to have that extra property disappears here. You can verify that in things in the essential image here because it's a tensor functor, so it has to send dualizable objects to dualizable objects. But the hypotheses guarantee that dualizable is the same thing as compact. So, yeah.
When you say rigid here, your notion is generated under dualizable?
No, I haven't said what it means, and it's not that. It's a
something.
Okay. So then the main theorem. So this is Efimov. K theory naturally extends to the dualizable categories. Meaning, the K theory functor from this thing to spectra, whatever you like, or Kn for any n, functor to abelian groups, canonically extends to a functor from this category to the same target. The K theory functor here factors through this included, meaning there's a bigger world in which algebraic K theory can be defined. For things of the form in C, it's just you pass to compact objects and take the normal K theory you know there. For things not of the form in C, it's not that. Something new and mysterious. Okay? And also, yeah, if C is rigid, then K of C gets a ring structure. So that, morally speaking, the tensor product on C induces a ring structure on K of C, just like usual. Okay, and now here's a nice fact that the inclusion from rigid, presentable, stable tensor categories into all presentable, stable tensor categories has a right adjoint. So we call it the rigidification. So now you see that these things really are everywhere. You take any tensor category you happen to run across, you hit it with this, you get something rigid, and surprisingly enough, it's very rarely compactly generated. You produce something genuinely new, even if you start with a very familiar one of these. Even if you start with one that's actually compactly generated, but not rigid, you apply rigidification, you get a new category, is rigid and not compactly generated. So really, these things are everywhere, and they're extremely, yeah, well, yeah. And so if the unit in C is compact, then even better, this C ridge is actually sitting fully faithfully inside C. And how to think about this? It's a C ridge is an improved version of taking end of the set of dualizable objects. in this case where the unit is compact. It's bigger than that, and it's not compactly generated. Okay. Again, I will say more about this and how it actually works when I get to the example I care about, but I don't want to say too much about examples that aren't in the focus of the talk because I want to get through some things. Okay, so now what are we going to do? I'm still in this section, candidate complete K of C. Oh, that one doesn't stick. Is this clock accurate, could I ask? I don't, my phone is out of batteries.
It's a couple of minutes past, it's
Okay.
5:01.
Thank you.
It's an hour.
What's that? It's an hour plus. Yeah. I'm in modulo 60. Yeah. Okay. So what we're going to do is we're going to produce, instead of thinking about trying to produce a small category and taking K theory of that, we're going to produce a large category. Take the K theory in this new sense. We don't even have to worry about producing a dualizable one. As long as we produce a tensor category, we can just rigidify it at the end. Now here's a experimental fact. If C is any reasonable, I mean, this is not a mathematical fact, right? This is, if this is any presentable stable infinity category with tensor product, whose objects feel like some kind of complete topological C vector spaces. Okay, there's millions of options for what you could mean by a topological complete topological C vector space, base it on Banach spaces, whatever, Hilbert spaces, whatever you want. But a fact, an empirical fact, is that whatever choice you make, once you rigidify, you always get the same thing. So you get something truly canonical. So all of the subtlety of infinite dimensional topological vector spaces, different kinds of convexity properties, whether you have Banach, open balls fundamental or compact set, the kind of dual thing where convex sets are fundamental. Once you can make categories that encode any of them, but once you rigidify, you always get the exact same thing. This is the main thing I want to advertise, is there really is a canonical choice for linear algebra in infinite dimensions, topological vector spaces.
So think of this as some version of the phenomenon that the finite dimensional vector space has a unique topology.
Sure, that sounds good. Yeah. Maybe I will from now on. So I'm the experimentalist, maybe you're theoretical. Yeah. Right. So I won't, so I will tell you I should say, preferred way of.
Just check. So this will be that you have everything is derived. This is including
everything's derived.
Experimental observations about how you resolve one kind of weird. Like this just include facts like how you would resolve like a Banach space by compact type things, or how you would resolve a compact type thing by Banach space. It has all these resolution facts in it.
Yeah.
It has nothing to do with C, I guess.
It also, well, I might get to non-Archimedean stuff at the end of the talk. It turns out in the non-Archimedean world, there's actually maybe two choices. But you're happy. There's a choice in the non-Archimedean world that doesn't exist in the Archimedean world, and it's the easier one. Okay. Other questions? Okay.
You can work with R.
Oh, sure. Yeah. No, I'm about to explain that it's extremely general. Oh, I'll use this. Yeah. So I'll give you our preferred big C tensor, which we can rigidify. So yeah, maybe I also take the opportunity to advertise that Peter and I are currently teaching a class on analytic stacks, where we propose new foundations for analytic geometry. And they're being posted on IHES's YouTube site and so on. So, and now I'll make contact with that course to some extent. So if, well, there's many different things you can start with as your familiar input data, but let me just take an arbitrary Banach ring with the norm specified. And from such a thing, you can produce an analytic stack in our sense. So liquid, so-called liquid analytic stack associated to this. And every such thing has a derived category attached to it. And it's one of these C tensor guys. But it's not rigid, but you can then rigidify it. And then you get something that, well, I claim that all the steps are canonical, but certainly this composition of steps is canonical. You might bicker a bit about how we set the foundations up, but it doesn't, the composition is certainly canonical. And so if this is a trivial norm, so basically if you're thinking of this as being discrete, then what is this? This dr triv liquid ridge. It's just the usual big derived category of R. It's compactly generated, and its K theory is the usual K theory of R. But now we fit it into a machine where we don't need to plug in a discrete ring. We can plug in a Banach ring, for example, and we naturally get something where we can take K theory. Okay. Let me give you a description of that. So when R is C with the usual absolute value, usual Archimedean absolute value. So here is a description.
Can I ask a question?
Just a sec, of the resulting rigid category. Yes.
But you don't really mean that every step is canonical. Like it still depends on P, right?
P?
Like this.
No. P's in the norm.
Oh. Okay, that's pretty good.
Like there's different norms you can put on R.
Yeah.
There's the usual one, and then there's the pth power for any P between 0 and 1. It matches up. Yeah, it's cool. Yeah. Okay. Right. So here is a description of the resulting rigid category. Right. So I'm not going to. So this thing lives inside there, but because that's not familiar, I'm going to instead embed it in something more familiar to describe this category. Something based on Hilbert spaces, which I think we can all agree on. Kind of nice enough things. So, and I'm going to call this the resulting rigid category. I'll call it analytic derived category of the complex numbers. So. So this, so you can put it inside, I'll write it as an in category of a bounded derived category of Hilbert spaces. Let's say separable Hilbert spaces. And here all short exact sequences split. This is like an exact, or split exact. Split exact category if you like. So you're just, it's basically just you take finite chain complexes of Hilbert spaces and then you pass to the chain homotopy category, except it's some infinity category version of that. And then you make it big. So you pretend like it's derived category and so on. So then it's just a full subcategory of that. And which full subcategory is it? It's the one that's generated under colimits and now I have to specify for you a nice class of more or less topological vector spaces. Well, yeah. Oh, I lost my other good one. Okay, generated under colimits by what are called the strongly nuclear dual Fréchet spaces. What are these? These are colimits of Hilbert spaces sequential co-limits, let's say injective maps, it doesn't really matter, where the transition maps, so each hn to hn plus 1 is a compact operator whose singular values decay rapidly. Okay, that's the canonical class of topological vector spaces. So faster than any inverse polynomial, or slower, or faster. So here's a non-example. So there are co-limits of Hilbert spaces. So they're things that feel like, in that regard, they feel like, say, distributions on a manifold. But a non-example is the usual space of distributions on any compact manifold. For example, S1, which is just the space of slowly increasing sequences. Again, slower than any polynomial. It's equal to rapid decay. So there's a funny thing. I mean, this is a basic example of what's called a nuclear dual Furché space. It's the absolute most basic one, but it's not strongly nuclear dual because the transition maps here are like, they're trace class, but they're not rapid decay. They decay kind of linearly instead of rapidly. So, but an example is if you take holomorphic functions on a K, where K is a compact subset, C to the D. So, complex analysis or power series based stuff is allowed, but C infinity stuff is not allowed, is the moral of the story. And this, or more generally, I'll just say that we're more generally, if you have solutions of an elliptic differential operator, if you have some complex elliptic differential operator on Euclidean space, and you choose a compact subset, you're going to have this condition on the rapid decay in the transition maps.
This category, let yourself use those kind of generators that you just mentioned.
Yeah.
How many of them do you need?
It's not quite clear. Yeah. Yeah.
And does this category have any T structure on it?
It does have a T structure. Yeah. So there's an abelian category as well, but it has some non-Hausdorff things in it, as it sort of has to. So these aren't this isn't an abelian category. Formal quotients of things like this would be an abelian category.
But things like this are in the heart.
Yeah. Yeah. The T structure is kind of very naive, you could say. Okay. Go over to my notes. This is the point where when I was preparing my talk, my son, I must have gone to the bathroom or something. My son came and drew a math monster. So I hope you all can see it out there. It's pretty nice. It's got numbers on his face, making a mean expression. Okay. He was enchanted by Halloween. Okay. So now I've told you what the category is, but I want to talk about K theory, but I didn't tell you how the K theory of Fimov works. So now let me do it in this example. So the resulting K theory, which I'm calling well, here's the trick, is that all of these, I said these dualizable guys are always close to compactly generated guys. And the more precise version of that is that you can always put them inside a compactly generated guy such that the quotient is also compactly generated. Well, that's actually kind of automatic. But yeah, so there's always the left-hand term in a localization sequence where the other two terms are compactly generated. So if C is dualizable, there exists a localization sequence. C goes to in D, goes to in D. And then K of C is just the homotopy fiber of the usual K theory, of the Phelan K theory of C, of the usual K theory of the compact objects here, I'm mapping to the usual K theory of the compact objects there. That's kind of how you can get your hands on it. Well, provided you accept that algebraic K theory of small categories is concrete, and just debatable.
But do you know what the D and the E kind of are?
Well, there's many choices, and it's an art selecting the right one. But but now in this case we know what they are. So now I can tell you kind of concretely. Yeah. So in our case, so we have our D. It's just this bounded derived category here, but that's also the same thing as the bounded. I mean, there's a single generator here, which is pick your favorite Hilbert space of infinite dimension. And then this category is just the same thing as the bounded derived category of the non-commutative ring this time with bounded operators on that Hilbert space. And when you calculate the quotient, it's also going to be generated by a single object, just the image of your favorite Hilbert space. But then the endomorphisms change. And what you get is, maybe I should say perf actually, just to be safe. Perf, be correct. Bounded operators on Hilbert space modulo a specific so-called Schatten ideal, which actually we've already encountered. This is the ideal of compact operators with rapid decay singular values. Okay. But this guy or this category is one of those types of categories I was talking about that has an Eilenberg swindle. So its K theory is 0. So at the end of the day, what you find is that this analytic K theory of the complex numbers is just a shift of the usual K theory of a rather strange ring, some analog of a Kalkin thing. So this bounded operators on the Hilbert space modulo this Schatten ideal. But let me make a remark that the ring structure on KNC, which is induced by the tensor product you naturally have on this category, it's obscure from this perspective. So this perspective isn't actually nice for, it's concrete, so to speak, but it's not necessarily the best way to understand what this thing is. Just I'm giving it to you for comfort. You can rewrite this thing up to a shift as the K theory of an ordinary ring. Okay. But now I've said enough maybe to say what the conjecture is. The conjecture. So I'll give it on the level of homotopy groups. So pi n of this analytic K theory of the complex numbers should be well, z in degree 0, and it should be C cross in degree 1. But probably the best way to understand this C cross is as uniformized sort of 2 pi I, C mod 2 pi I z, following Deline, I guess. And then more generally, when n is like 2m minus 1, you should write this as 2 pi I to the m z. But then if n is 2m, and this is for m positive, but if n is 2m, m positive, you should get 0, generalizing our discussion about K2 of the complex numbers. So this was exactly the regulators, right? And then you should get z if n is 2m and m is less than or equal to 0. So there should be stuff in negative degrees as well. It's an aspect I didn't mention that once you go to this idempotent complete context, then K theory naturally has stuff in negative degrees as well. Okay, so yeah, so let me note. So this.
Odd negative degrees.
I'm sorry?
How about odd negative degrees?
Did I not mention that? Wait, oh, thank you, 0, yeah.
You mean z or 2 pi I something?
Ah, thank you. Yes, I mean 2 pi I to the m. Thank you. Yeah. So note, so this suggests that so in terms of like thinking of K-theory in terms of X in some other category, this suggests that K-theory is like I won't bother trying to make it precise, but X in the category of pairs. So L filtration on the complexification. So this is a abelian group, and this is a decreasing filtration on complexification. So it's kind of mixed Hodge structures without the weight filtration, you could say. Okay, and now I want to say something about the evidence for this conjecture.
Does the construction give these K groups only as abstract groups, or do you see the topology on them?
In principle, you only see them as abstract groups, but let me address that more later.
Negative case. So I understand x can have something to do with kn for n positive,
yes.
But what about negative one?
So it's also X. I mean, there are HOMs. So in this category, I mean, there are HOMs from Z to Z minus M, right? Yeah. So it's not X, yeah, it's HOMs. Right, so the evidence, the first bit of evidence is that it's proven true. That's, I guess, the theorem of us, in degrees less than or equal to 0. So the part where you're just getting Z's and 0. And also it's probably within reach in degree 1 to see that you get the C cross like you expect. It's not obvious by any means, but it's probably within reach. Another thing is that there does exist a comparison map, natural comparison map from so Kn analytic C to the expected target, expected value. So extending the regulator maps basically. So the usual K-theory, algebraic K-theory of C kind of maps to this naturally. This would be if you did the naive thing of taking your category, taking compact objects, and then taking K-theory instead of taking this better thing. This is the regulator. In fact, so there exists a commutative square of rings in the spectra. So KNC goes to, well, let's do this one first. KU, that's the topological K theory. That would be if you just had the Z's or just if it was just 0Z, 0Z, 0Z everywhere. And then you have to add in some de Rham data. So you can use, for example, negative cyclic homology, say over the reals, it doesn't matter. The complex numbers, or periodic cyclic homology, the reals of the complex numbers. So this is like topological or Betty. This is like de Rham. This is de Rham plus filtration, so to speak. And then the conjecture, the real conjecture is that this is a pullback, or the honest version of the conjecture, a spectrum level version. Right. Another thing, I'm not going to get to the non-Archimedean evidence, although it's interesting. Maybe I'll just say it in words while I'm erasing. There is a non-Archimedean analog of this, say for CP, You can identify everything. You can prove it using a theorem of Sasha's, Fimo. Then using this theorem, you can do a calculation and actually confirm the analog of this conjecture for CP. Or a variant, maybe solid variant as opposed to liquid. It's it's fun. You see period rings popping up.
Subscript R.
Where are we?
That bottom board. HC minus sub R.
Oh, the real numbers.
Does that affect the?
Well, you don't want to do it over the rational numbers.
But over C.
Yeah, over C it's the same as over R. Yeah, I mean it's a tall. To me, it feels more principled. Because in principle, this is a more refined thing. But of course, it's the same. So, but anyway. Yes, and here. So, by the way, does this address your question earlier in the talk? Okay. So also this Kn functor, it actually extends in two different directions. So it extends to arbitrary complex analytic spaces. And then the conjecture is that KMC is compactly basically related to, in the same way that K theory is related to motivic cohomology, compactly supported Deligne cohomology. But it also extends to arbitrary, let me just say smooth, although it's not really necessary, complex algebraic varieties.
Complex.
Oh, thank you. Sorry. Yes. Okay. It's a complex analytic space. Thank you. And then the conjecture is that K theory analytic is some version of Deligne balancing cohomology. Note that if you take an algebraic variety, you're getting a different value for it than its analytification, which is natural. But so you're taking the base C to be always analytic in the sense that you're remembering the topology. But when you do things over it, you can choose whether they be algebraic or analytic. You get different answers. This, so that I'm supposed to be giving evidence, but this is just another. But the point is that the functoriality and the projective bundle formula all match up. So the functoriality you see in compactly supported Deligne cohomology, whichever directions you have it, you get it over that. You can prove it exists here, and same with Deligne balancing and over here. So they feel the same in that respect.
The second
No, you don't get compactly supported in the second case. So there's a good reason why, but I won't get into it. Okay, and also this kind of geometry goes into the proof that it holds in degrees less than or equal to 2. So sorry, less than or equal to 0. So we use this extension to complex analytic spaces to get a handle on what's going on over a point. So in that sense, it's kind of a fluid sort of formalism. And this, now I can address your other question about whether there's extra structure on these. Yes, there is. They're all sheaves on complex analytic spaces, which is stronger than having a topological structure. So it's A1, yeah. Conjecturally, it would be something like A1, yeah. A1 analytics. Yeah. And the last thing I was going to talk about was non-Archimedean analogs, but I think I won't. So thank you for your attention. Questions?
So a very vague question. Like,
Yeah.
why do we not have like negative cohomology for like discrete fields, but we do have negative K theory here.
No, even for CP, there's nothing in negative degrees. And it's just something, there's something about those complex numbers It's really not obvious. It's not obvious why. It has something, I mean, it has something to do with the Betty realization. They have this, it's nowhere else do you get a, I don't have a good answer, as you can tell.
We replace C by R.
Yeah. Oh, you would just take fixed points for Simon, Galois group acting.
So it is related to the poles of the gamma function.
Sorry?
It's related to the poles of the gamma function.
Well, yeah. No, I mean, this is, yeah. And so, this kind of thing is what should be related to regulators and.
But regulators, it's positive integers. So I'm speaking of the negative.
Yeah, no, but this year, I think you want these guys in the negative degrees as well. You think about the whole L function, yeah.
Say a few words about how these definitions would compare with more classical definitions in the K-theory of operator algebras.
Yes, thank you for that. I'm happy for the opportunity. They proved some very interesting theorems. For example, if you take, thanks a lot. If you take, I was looking at K-theory of bounded operators on a Hilbert space modulo this Schatten ideal. If you look instead at K-theory of bounded operators on a Hilbert space modulo the ideal of all compact operators, then this, and you take loop space, say, and this is KU.
Wait, algebraic K-theory?
Yep, algebraic K-theory. Yep, no, it's it's amazing. Yeah, but so what's the difference? Well, the difference is if you have a compact operator, you can't define a trace. If you have a trace class operator, or even better, a rapid decay operator, you can define a trace. And that's why this is picking up more over here. There has been investigations of the analog where you replace this by the Schatten ideal P for P positive. There have been some, I think it's a theorem of Cortinius and I hope Tom, perhaps, I forget, please don't quote me on it, but that maybe the fiber of the cyclotomic trace here is also KU. And it would be very interesting but their methods unfortunately do not reach this, which is the truly canonical thing. But it would be very interesting if there was some way to leverage their results valid in the P greater than 0 regime to get something here. So the reason this isn't good is because it doesn't correspond to a dualizable category really, and it doesn't, or a rigid category. This is, unfortunately they haven't investigated the only, the truly canonical thing, but they've done a bunch of interesting related work which could serve as stepping boards for understanding this thing. Yes.
So you kind of said that this description is bad because of the ring structure, but then the kind of list you gave, you didn't at least talk about the ring structure.
I didn't talk about the ring structure there. Wait,
you didn't. But so then, which means that you could still address, since you didn't talk about the ring structure, you could still address that table from this thing conceivably.
I don't understand. It didn't sound like a question.
Can you? You said that you prove these negative results using a totally different method. But you have.
Sorry, no, I didn't even understand that. Sorry.
Well, you have a description of the analytic K theory there.
No, it's conjectural. Yeah. Wait, no. Oh, this. Yes.
A description.
Yeah.
And you gave some answers.
Conjectural.
No, but some of them you said you proved.
Oh, yeah.
But can you see them? Can you understand them at all in an operator theoretic way yourselves?
Probably.
Can you see where those classes are coming from in this optic?
Wait, it's not fun. So it was Karubi, I should say, who found the degree -2 class here. And you can use his method to find show the same class lifts to here. It's fun. It's kind of the inverse to the Bott element. And the Bott element itself doesn't exist because we haven't passed to homotopy yet. But it's a bit of a slog. But we have a clean geometric way of producing the same class. Okay, once you have that, then yeah.
So you said it's a shift in analytic topology. So if I take Stein manifold and consider its analytic K theory and conjecture, I should get quotient of homomorphic functions.
Exactly. Yeah. You can. It's just there's no shift cohomology in the hold the wrong part of the lead cohomology. So you can write down what it is.
You mentioned there is a cyclotonic trace map.
Yeah, sure. Yeah.
Can you describe the target?
Oh, that's it. Thank you. Another, yeah. Okay, here's a companion conjecture. Let's just talk about Hochschild homology. I mean, it's actually over Q, right? It's a Q linear category. So forget cyclotomic. It doesn't do anything. But the companion conjecture, it's about the Hochschild homology over sphere spectrum Z, Q, it doesn't matter, of this, well, let me say for this ring. It's just, well, maybe I want to say suspension. So it should just, for the Hochschild homology of the category I'm interested in should just be C in degree 0. And that should correspond to the fact that you can take traces. So, but actually this again unwinds to something that looks completely unbelievable, that you can, this is a non-unital ring and you can make the Hochschild complex there, and that computes the thing, the loops of this. And it's really the algebraic Hochschild complex of this ring. So you're tensoring this ring together over Q and making the usual Hochschild complex. And the claim is to say cyclic in positive degrees. And the non-Archimedean analog of this is equally unbelievable, but it was proven by my student, Adriano Cordova. So take compact and trace class is all the same in the p-adic setting, but you take the Hochschild complex of this thing with algebraic tensor products, and you get QP in degree 0 and you get 0 in positive degrees. His proof does not go by analyzing this Hochschild complex. It uses a whole bunch of crazy stuff, including the Pimage results, and then just McCarthy and all sorts of nonsense. But yeah, anyway, that's, yeah. But you could, in principle, just try staring at this Hochschild complex, and you'll, if you manage to prove it, say, cyclic in positive degrees, then you'll be halfway to proving our conjecture. So give it a shot. Yeah.
The multiplicative structure is the only reasonable one from the.
Yes. Yeah, and I mean, one of the reasons I like this is because it kind of makes it plain. But yeah, there's also a tensor structure on this category, and you know the Tate twists are multiplicative in the appropriate sense, that kind of.
So if you do lift that class, the -2 class up,
yeah.
Can you then see that its products are like that its higher powers are non-zero by regulating them in some way, and then like you at least get a kind of embedding of the answer into the thing.
I'm sorry. Once again, I'm having trouble understanding your question.
Well, you lifted the -2.
Yes. Yes.
Then you could take its powers and,
yes.
And you're allegedly generating all the negative stuff.
Exactly.
But can you see those all non-zero by regulating it, hitting them with?
Oh, you detect them. I mean, yeah, but that's not really how the proof goes. I mean,
no, I know, but I'm just trying to.
Yeah, you can detect them in topological K theory. Yeah, but it's not right. It's not about regulators at that point, because there's no. This is where the regulators really are. It's the ambiguity in the regulator that's kind of the integral thing.
So the conjectures concerning the varieties, criteria of analytic and multiplied varieties, so the dynamics of this conjecture.
Correct.
So at the bottom there is Bernison, that's symptomic, I guess.
It's not so. It's some form of it. Yeah, some form of it.
And at the top, what is that?
That's a good question. So at the top, I would say that you'd have to be in some dagger context, some kind of, or some whatever, you know what I mean by this. Yeah. And then it would probably again just be compactly, yeah. No. I guess the answer is I don't know. Yeah, but it should be possible. Yeah, I'm sure if I think I can answer it, but not right now. Yeah.
And is this diagram supposed to be valid for any x also?
Yeah, if you put like KU of x here, and yeah. Exactly.
Sorry, for algebraic varieties.
Oh, no, sorry, only for compact analytic varieties. Yeah.
Or even the diagram is valid just for compact.
Correct. Otherwise, you'd have to put the compactly supported variants of all of the things. But okay, I mean, it also depends on what exactly you want to mean by this. There's a non-compactly supported variant too, but it's not directly the K theory of something. So I mean, by sort of Poincare duality, you can always get one from the other. Or not even Poincare duality, just sheaf theory.
So here you said the functoriality matched up.
Yeah.
Like do you have like push forwards for immersions for like rigid quasi-coherent sheaves?
Look, I don't remember the details of anything, but yeah, I checked all the functorialities. They all match. I mean, whatever happens, if you have one here, you have one there. I mean, yeah. So I mean, maybe I can say something a little more helpful than that. I mean, we have also this 6-functor formalism for these for this theory of quasi-coherent sheaves we built on analytic spaces. And so when you're supposed to get a map on K theory, you're supposed to get one when you have a functor which commutes with colimits and whose right adjoint commutes with colimits. So an example of that would be if you have a smooth map and you take lower Schrieb, right? But another example of that would be if you have an arbitrary map, what was I saying? If you have a smooth map and you take lower Schrieb, yeah. Another example would be if you have a proper map and you take upper star. So this, yeah.
Okay. If no further questions, let's thank the speaker again.